going to take a look at buffers. And I have my 1-year-old son next to me, which you might hear. Okay, buffers are solutions that can resist drastic changes in pH that would normally happen when you add a strong acid, which is a source of H+, or a strong base, which is a source of OH- to a solution. So how can you create a buffer? Essentially, you want to take advantage of an equilibrium situation so that you can apply Le Chatelier's principle. The reaction can shift to the left or to the right, whether you add an acid, a strong acid, or a strong base to the solution. So let's take a look at this equilibrium below. So this is a weak acid ionizing into H plus and its conjugate base. Now we know weak acids don't 100% ionize, so we would always put those double arrows to show equilibrium. And then we can harness Le Chatelier's principle if we have changes in H plus concentration. So if you were to add a strong acid, which is a source of H plus, this reaction could shift to the left to use it up and also use up A minus and create more of the acid. If you were to add a strong base, OH minus, then the H plus would react with that OH minus, it would go down, and the HA could shift to the right to create more of it, and also to create more to resist further changes with adding more strong base. So essentially, you need to make sure that you have a roughly equal mixture. You want both HA and A minus present so that it can shift one way or another. And you want large concentrations so that they can resist changes enough. And you want to make sure that you have a weak acid and its conjugate base present. Again, weak being a really key word here, because if you were to have a strong acid, that would 100% ionize. You would have an arrow all the way to the right, and it wouldn't be able to go in the reverse direction because its conjugate would be of negligible strength and not able to accept that H plus and act as a base. So you need to make sure you have a weak conjugate acid base pair. And you could do the same thing with a base, and you might want to change the reaction in your notes if you don't have this one, because this is what we're used to working with. A base, showing it act as a base, you make it react with water, and you'd get the conjugate acid and OH minus. If you were to add a strong base, that's a source of OH minus, that would shift the reaction to the left and use up that extra OH minus. If you were to add a strong acid, that would react, the H plus from the strong acid would react with the OH minus from here. It would use up this OH minus, the reaction would shift to the right to supply more OH minus that used up. So this could create a buffer solution as long as I add both the base and its conjugate acid, or vice versa, the acid, the weak acid, and its conjugate base. But again, this has to be a weak conjugate acid-base pair. We want roughly equal concentrations of both, and we want large concentrations so that even if some of the HA gets used up, we still have a big pool more of it. So we need an acidic species and a basic species, and it needs to be a weak acid-base pair. Now, if you remember, something like a weak acid, something like HF, is only going to ionize a small amount. So just adding HF, just adding your weak acid into the solution isn't going to be enough to create a buffer. We need a source of the conjugate. So how do we get that conjugate into solution as well? We are typically going to be adding it in the form of a soluble salt. So remember your solubility rules. Group 1, ammonium nitrate, always soluble. So if I were to have, let's say, a 1 molar solution of HF, I should also be adding a soluble salt like NaF to it, or have 1 molar solution of NaF, so that this way I also have a source of the conjugate, because just adding the weak acid isn't going to be enough to provide enough of a concentration of that conjugate base to really make it function as a buffer. So again, typically it'll be in the form of a soluble salt. And your blood is actually a buffered solution. It functions in the pH range somewhere like 7.35 to 7.45. So to recap, you want a weak acid and conjugate base pair. You want roughly equal concentrations of that weak acid and a source of the conjugate base, like a soluble salt. And you want a weak base and its conjugate acid, vice versa. And you want relatively large concentrations of each. The larger, the more ability to buffer. And what you're going to notice is a lot of these buffered solution problems are going to look just like those common ion problems from the last lesson, because you have a source of the in this case the weak acid, and a source of its conjugate base ion, you have a common ion problem. As I was saying before, you want something that's going to resist changes in pH, so you want something that's going to react with the base or react with an acid that's added to your solution. So you're really, again, just looking at the ionization, okay, as we've done in other problems. Your acid can ionize into H plus and A minus, your conjugate base. That H plus would react with OH minus from a base to create water, and the H pluses, if I'm just looking at an overall reaction, here's what's really happening, and that's what I put that here, what's left with what's happening all in one step. The weak acid can react with OH minus to create the conjugate and water. That's just what we talked about before, but showing it in one step. Again, the takeaway here is you want pretty large initial concentrations, so that way you have a large buffering ability that even if you add more acid or add more base, you still have a roughly equal amount of acid and conjugate base, so that ratio won't change very much, and vice versa. So what do I mean by this? Let's look at this in more of a visual. If you have your acid and conjugate base, here's your buffer starting with relatively large and equal concentrations of both. If I add an acid, a source of H plus, the F minus would react with it, right? It would accept that, it would act as a conjugate base, accept the H plus, and turn back into HF. So HF concentration would go up, F minus would get used up, that would go down. But as long as I have relatively large concentrations to start with, that change would be almost negligible. And they are still, if I look at this, they're still roughly equal. So that's why I want to start with large concentrations. And vice versa, if I add OH minus, the HF could react with it, as shown down here, pick it up, turn into the conjugate base. The F minus would increase, HF would decrease, but again, as long as I start with relatively large and equal concentrations, that change won't be super substantial, and this can resist large changes in pH. Okay. Buffer capacity is the amount of acid or base that can be neutralized by the buffer before any significant changes in pH occur. So obviously a buffer will only have a certain ability to resist enough changes in pH before before you might run out of either the conjugate or the conjugate acid or base. So buffering capacity is how much it will be able to do that. So it's going to depend on how much initial concentrations of acid and conjugate base you have. The greater the concentrations to start with, the greater the buffer capacity. So the buffer capacity directly depends on how much you have to start with in terms of concentration. For these buffer problems, you can use this Henderson-Hasselbalch equation, which is on your formula sheet. You'll see it over here. pH is equal to the pKa of your acid-base pair plus the log of your conjugate base over your initial acid. And remember, these square brackets mean concentration and molarity. This is actually just derived from that Ka equilibrium expression that is on your formula sheet as well. It's taking the log of both sides, so the log of Ka becomes pKa, the log of H plus becomes pH, and then you get the log of this ratio, A minus over HA. So it's really just derived from that. Sometimes you are dealing with, instead of the ionization of a weak acid, you could be dealing with the ionization of a weak base. So just remember that your base component is on top and your acid component is on the bottom. So if you're looking at, let's say, NH3 and NH4+, you might want to kind of just remember the base component goes on top, acid on the bottom, because this is always kind of written in favor of the acid ionization. So let's look at a problem. And these problems are really just going to be like those common ion problems that we just did in the last lesson. Take a moment and give this a try. With this, you can actually do either an icebox or the Henderson-Hasselbalch equation, which we showed on the last slide. And that equation is something that you can actually use going forward for any of these common ion problems to make them easier. It's just a shortcut. It's, again, as I said, it's really just taking the log of both sides of this equation. So what's always helpful is to kind of write an ionization for what's going on first. So your buffer solution is always going to be an ionization of a weak acid turning into its conjugate base, or vice versa. So here I'll notice that this is NH3 is my base, and here it is with a salt, which is a source of its conjugate acid. Notice the salt is it's a strong electrolyte. It's going to be something that's completely soluble, so that it's a good source of my conjugate NH4+. I have 0.4 molar of NH4+. So here's my reaction that's going on. This base, let's make it act as a base, so we'll make it react with water and release OH minus and NH4 plus, just as I would do for any weak base problem. I would write the ionization of it acting as a base. And if this were an acid problem, or an acid and a salt of the conjugate base, then I would write the ionization of the acid. So I'm just doing it just like any weak acid or weak base problem. Okay, but what I'll notice is I can actually use that Henderson-Hasselbalch equation. I have everything that I need except for the pH. I have a Ka. Well, I don't have a Ka, I have a Kb. Uh-oh, what do I do? Oh, well, I know that Ka times Kb equals Kw, so I can actually find the Ka and this equation was on your formula sheet too, and I can use the Ka. So notice that even though this is a base system that I'm kind of starting with, a base on my left-hand side here, I still need a Ka. And I can do pKa by just taking the negative log of that number, and I get 9.25. I have my concentration of my base and my acid component here. 0.25 is the base, so that'll go on top. 0.4 is on the bottom, and I took away the units, you'll notice, because molarity over molarity cancels out. And if I solve, I get 9.05. If you want, you can do this just as any other problem that was common ions with an ice box. So I can take this ionization reaction, I don't care about water because it's a liquid, and I can put in my initial 0.25, 0.4. So notice it's just like a weak base problem, except I have some conjugate acid present too. It's like one of those common ion problems where I don't have 0, 0. I have a source of my conjugate. And I do minus x plus x plus x, and I don't know anything in equilibrium, so these could be in terms of x, but I can use that 5% rule if you go back to the K in the last problem, or in the problem statement. Okay, the difference between the initial and the Kb is definitely 1,000 times or greater, and I can assume that, hey, x, the amount of OH minus, is going to be almost negligible compared to both the 0.25 that's present and compared to the 0.4 that's present. And I could say that this is going to stay close to 0.25 even if I subtract a very, very small number, and this is going to stay close to 0.4 even if I add a very small number. And then I can plug into my Kb expression. Okay, make sure it's the Kb expression because this is showing the base. And I get 1.1 times 10 to the negative 5 for my OH minus concentration. I didn't finish answering the question. Get the POH by taking the negative log of the OH minus, and I could subtract that from 14 to get my pH, which would be the same as the last, showing the last alternate method. So either way is totally fine. And notice that 1.1 times 10 to the negative 5, if I do 0.4 minus 0.000011, it is essentially 0.4. This approximation was okay. If you want to find the percent ionization to check the 5% rule, feel free. Okay, and what you'll notice, there's some implications of this. Okay, so for buffering system, all solutions that have the same ratio of the concentration of the conjugate base over the acid are going to have the same pH, because if this fraction is the same, you'll get the same plus log number, and this will end up being the same pH. Optimal buffering is actually going to occur if the concentrations of the acid and conjugate base are equal, because then this would be the log of 1, log of 1 is 0, and then the pH would just equal the pKa. If the fraction here starts at 1, it's actually not until the ratio changes by a factor of 10 that a pH change of 1 unit would occur. And that's what makes these resist large changes in pH. The pKa for a weak acid should typically be as close as possible to the desired pH. This way you can use roughly equal and large concentrations of HA and A-. That's what we said would make the best buffering system. So you want to pick something where the pKa is already close to the pH that you desire. So take a moment, try this example. Pause the video. Okay, so if you want, the chemist wants a solution buffered at 4.30, we want to find an acid where the pKa is close as possible to 4.30. So take the negative log of all these Kas and you'll find that benzoic acid has the pKa closest to pH, because that would allow us to use equal concentrations of HF or HA and A minus, and which we said would make optimal buffering. Okay. If your desired pH is less than the pKa of your acid, okay, if your pKa of the acid is higher than you want, then you're going to end up needing more HA form present. You want a larger denominator so that this is overall smaller. So the acid form would end up having a higher concentration than your base form. If your pH that you desire is higher than your pKa is too small, smaller than you want, then you're going to have a higher component of your base present. Your base form is going to have a higher concentration. And if you want, you can memorize that, but you can just figure that out logically from this Henderson-Hasselbalch equation. Take a moment and try this example related to that. A chemist needs a buffer solution at 4.30. Let's rationalize, and these are the same acids as before, about the relative concentrations of the acid form versus the base form at this pH. So you're just comparing your pKa to your pH. Okay, if your pH here, in this situation, the pH is higher, okay, it's 4.30 versus 2.87, so I'm going to need more of this conjugate base form present. I'm going to have more of that present in my solution in order to get the desired pH. Okay, here this pH is the pH is lower than my pKa, so I'm going to have more of the acid component present. Okay. Here I would have more conjugate base because the pH is higher. Here the pH is lower, so I'd have more of my acid form. Take a moment, try this, do now, pause the video, and then you can check your work, which this kind of goes through all the concepts that we talked about. Well, let's go through this example, which really helps to kind of review all the concepts of a buffer system. So you want to create a buffer solution using 1 molar HClO. Okay, on first glance, this is a weak acid. It starts with an H, it would ionize into H+, and its conjugate base, ClO-. This is hypochlorous acid. So if I want to create a buffer solution, I not only want to have the acid present, the weak acid present, but I want to have the weak base too. Remember that you want to make sure that you have a weak buffer system, a weak acid or base, because you want that equilibrium situation. You don't want to have a strong acid, strong base system, because then you wouldn't have an equilibrium situation. Remember, for those, we do one arrow all the way pointed to the right. So it's important that this is a weak acid or a weak base that is in your buffer system. So if this is a weak acid, then I'm going to want to, add the conjugate base. And how can I add this conjugate base? What could be my source of it? I would want some type of salt that's soluble. I'd want a strong electrolyte. So something like, and you can take away this negative sign because this would be neutral at this point. You'd want something like sodium hypochlorite or potassium hypochlorite or ammonium hypochlorite, remembering your solubility rules, group 1, and ammonium and nitrate always soluble. And I'd want a roughly equal concentration, large and equal concentration, so let's also make this 1 molar. Now, if they ask for the dissociation, it's just showing the weak acid acting as an acid, releasing H+ and its conjugate. And remember, this is an equilibrium situation, so that this way we can apply Le Chatelier's principle. If H+ goes up, it shifts to the left. If H+ goes down, it shifts to the right. And that's why I was saying it's really important that for a buffer system, it's a weak acid-base pair. It can't be a strong, because then you'd have strong and something negligible. It wouldn't end up going in reverse. Okay, what effect would adding an acid have? Acid provides H+, a shift to the left, ClO- would go down, and HClO would go up. If I were adding a base, the OH- from the base would react with H+, H+ would go down, this would shift to the right, and ClO- would go up, HClO would go down. If I give you the Ka for this system, I can plug into that Henderson-Hasselbalch equation. So if equal molar amounts, meaning equal concentrations, equal molarities of the acid and conjugate base were used, what would be the pH? Well, the log of this ratio would just end up being 0, because these would be equal to each other, and the pH would equal the pKa, which would be 7.54, just taking the negative log of this number. If the concentrations of the acid and conjugate base were both to double, the buffering capacity would increase. I would be able to resist changes in pH for a longer duration of time, or resist more concentrations being added. We said the more we have to start with, the better it can function as a buffer. The pH, however, would not change. It would stay the same. Okay, because if I go back to that Henderson-Hasselbalch equation, the ratio of acid over conjugate base, or base over conjugate acid, whichever way you're looking at it, that ratio is staying the same. So the log of that number is still the same number. So the pH doesn't end up changing. And again, you can go to the Henderson-Hasselbalch equation to look at that. So it's important to know these kinds of concepts related to buffer system, and the AP likes to ask a lot of these types of conceptual equations too. And any of the mathematical calculations, you can use the Henderson-Hasselbalch equation, or you can just treat it as an icebox. But remember that it should be a weak acid-base pair so that you have an equilibrium situation, because that's what you need. It's just like these acid-base problems, except you have both the acid and conjugate base present.